Hi, welcome to the second lecture, and actually for technical reasons, welcome to the first part of the second lecture. There are going to be two videos. For technical reasons I can't get them all into one file for some reason. Anyway, this is the last of the pre-calculus stuff, and it's got to do with exponents and logarithms. And we're just going to be talking here in this particular video about exponents, and the next one, which is connected to this, is logarithms, so please watch both of them before class on Monday. So we'll start with the laws of exponents. I'm not going to go through them in all their gory detail. You can read about them in the book. You've already been through them. So I just want to highlight the important things about them. In particular, I want to highlight the things that people do sometimes to try to use them erroneously. So one of them is this one that says that if you take two numbers and multiply them together and raise that to a power, then you can rewrite that expression as the first number to the power multiplied by the second number to that power. And most people would probably get that right in particular examples, like 2 times x to the fifth is 2 to the fifth, x to the fifth. That's all safe and sane. But what happens sometimes is that people will look at an expression like this, a plus b to the 1.7 power, and then they'll think, oh, I can take a to the 1.7 and b to the 1.7 and do something with that, like adding them together. And that's absolutely wrong. There's nothing you can do to relate a plus b to the 1.7 to any of this. And so there's another rule that you might want to say to yourself that says exponents do not distribute over addition. You probably should say this to yourself at least 3 times a day until you never ever make the mistake. Exponents, it turns out, play well with multiplication. So you can multiply two numbers together and raise that to a power, and things happen the way you expect. Even works with division, right? If you go a over b to the x power, that's a to the x over b to the x, no problem. But when you've got addition or subtraction, you can't distribute the exponents over the addition. That works the same way with radicals. If you had the fourth root, this happened the other day, if you had the fourth root of a to the fourth plus b to the fourth, for example, there is such a tendency to distribute that fourth root, but this is just a to the fourth plus b to the fourth raised to the 1/4 power, and exponents do not distribute over addition. So you're kind of stuck with that. If you could factor that a to the fourth plus b to the fourth somehow, then maybe there's something you could do and make it into a different expression. But as it is, you're kind of stuck with it. Okay, another law of exponents that comes up all the time is this one. If you take two numbers, a and b, or a and to the x power, and multiply that by a to the y power, multiplying two numbers together with the same base, you get to add the exponents. And again, that's easy to see. If you just plug in a number for a, like 2, and raise it to the third times 2 to the second, you can see that this is 2 to the fifth. Well, according to the rule, it's 2 to the fifth, but that would be obvious if you just multiplied all the 2's out. There's 3 of them here, and then 2 more of them here, and that's a total of 5 2's. So that's kind of a reality check. It's not going to work if you try to do a to the x plus a to the y. You cannot combine the a's and the x's and the y's. And some people who would try to do that with 2 to the third plus 2 to the second and write that as 2 to any power, it's pretty clear that that doesn't work. On the other hand, there is something you could do with this. If you felt like it, you could factor out a 2 squared, and that would leave you with a 2 to the first plus a 1 for that second term. And occasionally that's handy. But exponents do not distribute over addition. So the best you can do is try to factor what's here to try to deal with that expression. Exponents deal nicely with multiplication. All right, but they deal even better with exponential expressions. So if you have a to the b to the c, that's an exponential expression, and exponents multiply in that case. So that will give you a to the power b times c. And that comes in handy a lot maybe backwards more often than forwards. For example, suppose that you had a 8 to the 4/3 power. Now, in order to do this problem, you have to remember one other thing. What does 8 to the 1/3 power mean all by itself, if that's a different problem? This is the cube root of 8. Raising something to a fractional power is a root. But what if it's a fraction like 4/3? What would that mean? Well, according to this rule of exponents, going from right to left, we could split 8 to the 4/3 as 8 to the 1/3 to the 4th, because 4 times 1/3 is 4/3. And 8 to the 1/3 is 2, so this would be 2 to the 4th, or 2 times 2 times 2 times 2, which is 16. So all of that is nice and safe and sane, and we don't have any particular difficulty with that. Unless you try to use rules for addition or subtraction with exponents, and then it doesn't quite work out. Let's turn our attention to the graphs of these things. We've already looked at the graph of 2 to the x, and I want to look at it again in conjunction with the graph of similar things. So here's 2 to the x. In fact, any exponential function pretty much looks like this. It's asymptotic on the left to the x-axis and then grows, and they all pass through this point 0, 1. So the question I want to look at, though, is how does the graph of 2 to the x compare to the graph of, let's say, 3 to the x? Well, that's easy, because 3 to the x and 2 to the x pretty much look alike, except 3 goes up faster from here, and it goes down faster this way. So 3 to the x is pretty much like 2 to the x, except goes up faster and goes down to the x-axis faster. So you could say that 3 to the x is pretty much, well, on the right side it's bigger, but on the left side they sort of switch places, because it's a stronger function, you might say. It just moves faster whichever way it's going. Goes up faster this way, goes down to the x-axis faster that way. One of the other functions that we'll be dealing with a lot is e to the x. And you need to know about e. We'll be looking at e in great detail. You'll know much more than you ever wanted to know about e. But for our purposes right now, e is approximately 2.7. e is a number. It's not a variable. And so to get e, well, we'll talk about how you get e. But for our purposes, what's e to the x? Well, e to the x is going to look just like this, except e to the x is crammed in between 2 to the x and 3 to the x. So you've got to think of e to the x as somewhere in there, because e, as 2.7, is between 3 and 2. So 2 to the x and e to the x and 3 to the x are related like that. Okay, that's one of the things that we can do with functions, with exponential functions. Another thing is to transform them in the ways that we've done with other functions, like flipping them. Here's a good example. 2 to the minus x. What would that mean? Well, as you know from any other function, if you compare f of x and f of minus x, that just flips the function horizontally, or vertically, excuse me, relative to the y-axis. So the graph of 2 to the minus x is going to be just like the graph of 2 to the x, except flipped relative to this vertical y-axis. So instead of it being asymptotic on the left, you're going to be asymptotic on the right, and this function is going to be decreasing, whereas 2 to the x was increasing. And the two are just mirror images of each other relative to the y-axis. So this one would be 2 to the x, and this one is 2 to the minus x. Okay? And there are other transformations, of course, that you could shift up and down, left and right, and we've done that kind of thing before. Okay? So I think we will pause here with exponential functions, and we'll get back with inverse functions and log functions on the second part of this video.